All right, so we're about to carry on with the wonderful world of intersections in three-dimensional space. So we've already managed to look at two lines intersecting, and we said that wouldn't happen actually very often unless I cooked the numbers real nice. And then last day we did a line and a plane, and we said more often than not that should work out. Well, today what we're going to look at is if we have two planes. Okay, so if we have exactly two planes, what could happen? Before we get there, I just need you to remember a little bit from grade 10 again. These are just lines, right? This is the scalar form of lines. And the reason we want to mention this, of course, is because we're going to look at the scalar form of planes in a minute too. So it says, how do the following lines compare to each other? They're all lines, right? They're all x and y. There's no z component there. And they're all in scalar form or standard form. And in grade 10, we were able to look at those equations and decide not necessarily just by looking at them where the point of intersection was, but we could decide if there was going to be a point of intersection or not. So hopefully what you're noticing, you're looking at those equations and you're comparing to see if they're multiples of each other. So for example, to go from the first equation to the second equation, we just multiplied by 2. Right? We multiplied everything there by 2. That means that the first equation and the second equation are actually exactly the same line. Right? They're written differently, but it's exactly the same line. So if in that case, if I said, what's the point of intersection of those two lines, you'd say there's an infinite number of points of intersection because they're the same line. They're right on top of each other. If you compare the first to the third, they're pretty close. If you're looking just from the 2 to the 8, we multiplied by 4. And the 3 to the 12, we multiplied by 4. But the minus 5 to the 1 didn't work. It didn't follow the same pattern. So when that happens, these planes, these lines are parallel. And I don't know how well you remember grade 10, but what would have happened is if you tried to set this up to solve for elimination, you would have tried to eliminate just one variable, and actually both variables would have disappeared. And you would have ended up with a situation where it says 0 equals 26, like we had the other day, right? And it's a situation where there's no solutions. And the only time there's no solutions is if the lines are parallel. So 1 and 3 are parallel. We said that 1 and 2 were the same, which means 2 and 3 then have to be parallel as well, I suppose. If you take a look at the fourth equation, it's not a multiple of anything, right? So this one here is very different. It's not parallel to any. And you can just tell that by looking at the coefficients of x and y. And if it's not parallel to any of the others, if we're dealing with lines, then they must have intersected at just one point. Okay, so again, we don't know where the point is, but we can tell just by looking at it that it intersects in one point. Okay, calling this 8.6a, problems involving two planes. We're going to have to spend a little bit of time looking at the intersection of planes. We're going to do just two planes first, and then we'll get into three planes next day. So possible things that could happen with two planes. There's actually not a lot. It says two distinct planes can be either parallel or else they intersect in a straight line. So parallel planes would be like the floor and the ceiling, or two walls, right? They would never intersect at all. So that's one possibility. The other possibility is that they could intersect in a line. That's easy to show if you grab your textbook and just open it up. You can sort of roll the spine any way you want. The spine becomes that line of intersection of the two planes, right? The front cover and the back cover. And the spine is your line of intersection. And that's the most common scenario, is that we'd get a line of intersection. Now, the way that's written there, which I suppose we have to be careful of, it does say two distinct planes. So there is a third possibility where the planes are actually exactly the same. And in that case, we just have planes that are multiple, or equations, I should say, that are multiples of each other. So we'll have to watch out for that. This is a tough one today. The calculations aren't going to be huge. What's tough about it is that we're trying to find a line of intersection. And we've never had to do something like that before. Whenever we've found intersections, we've been finding a point, right? Two lines intersected in a point. A line in a plane intersected in a point. In this case, we're trying to find the line where these two planes intersect. And the only way that we know how to write a line in 3 dimensions is to use our vector equation or possibly our parametric equation, which is what we're going to use today. So as we're trying to find that line of intersection, our goal will be to get something that looks like this. And I need you to keep that in mind because all of a sudden we're going to stumble upon an answer and it may not be obvious that we're actually at the answer when in fact we are. So we're trying to get a situation where we can write x equals something plus something t. And t is just a parameter, right? T is just any old number that I want. So t is some variable. T is the tricky part actually in this. So here's how we're going to start. We've got 2 planes there. And I'm actually telling you that this is the intersection. Okay, the line of intersection is described right there. X equals 0 plus t, y equals minus 3 minus 5t, and z equals 1 minus 2t. That's the answer. In a minute, I'll show you how we're gonna find it. But first, I want to just convince you that it really is the intersection. The way that you convince yourself that it's the intersection, if it's the line of intersection, it would be a line that is directly on both planes. So is the line on pi 1. Notice I called this equation 1 pi 1, pi 1 standing for plane. We use L1 for line. The reason we don't use P1 there is because we usually use P for point. So pi 1 is representing our first plane. So I'm going to treat this like we did in the last lesson, I should say, trying to find the intersection of the line and the plane. And what we did was we subbed the parametric equation in to the scalar equation of the plane. Whoops. So I'm considering line 1, or excuse me, I'm considering the line that we were assuming is the point of intersection and the plane. And if I try and solve this, you get 3t there, 5t. And if you put all of that together, the 3t, the 5t, the 8t, that's 0. 3, 4, and 7 is 0. So we get 0 equals 0. Or if you'd rather, 0t equals 0. Either way, that's the situation where there was infinite solutions. If there was infinite solutions, that meant that the line really is sitting right on the plane. Okay? Then you'd go ahead and do the same thing, and I think I'll leave this for you to try. Is the line also on the plane? Is it on the second plane? And it is too. If you sub it in, you'll get exactly the same thing. That's something you should probably try, but I'm going to move ahead just to save a little bit of time. If you sub that into the second plane, you're going to get the same scenario. You'll get 0 equals 0. So that proves that this line is on the second plane as well. And if it's on the first plane and the second plane, it must be the plane of intersection, or that must be the line of intersection. So how are we going to find it? How are we actually going to go ahead and get it? There's the same 2 equations. Okay, so we're still aiming for the same answer. We want to get that line. The problem we have this time is an opposite to the problem we had before. We used to have some equations where we had 3 equations and only 2 variables. And in that case, we were able to solve what we had to check in the third equation. This time we have 3 variables, x, y, and z, but we only have 2 equations. So we don't have enough, right? We're short 1 variable. What that means is that it's going to be impossible to solve explicitly for all 3 variables. You can't get an answer of x equals this number and y equals this number and z equals this number. It doesn't exist, right? There's an infinite number of solutions for that line of intersection. So what we're going to try and do is we're going to try and rearrange the equations basically. We're going to try and write 1 variable in terms of the other variables. So I'm going to get rid of Well, you know what, I'm going to get rid of this. That way we'll have a little bit more room. So step 1 says eliminate y, and then write z in terms of x. So I'm going to write the equations down again. 3x minus y plus 4z minus 7 equals 0. And x plus y, this is going to be that situation where I was saying substitution and elimination become really important for us, right? I want to get rid of those y values, and so I'm going to add the equations up. When I add them, I'm going to get 4x 2z minus 2 equals 0. So I've eliminated the y. I've written it as that equation. And then it says write z in terms of x. Write z in terms of x. So what that means is that we want z by itself and x on the other side of the equation. So I'm just going to start rearranging this. Leave the 2z there. I'm going to bring that 2 over, so it becomes a plus 2, and bring the x over. That'll be a minus 4x. And I want the z by itself, so I'm going to divide both sides by 2. So I get that. Z equals 1 minus 2x. So that was step 1. And that was what I needed to do. Step 2 says to eliminate z and then write y in terms of x. So I'm going to do almost the same thing, but I need to get rid of the other variable instead. So if I want to get rid of these z's, they aren't quite as easy to get rid of just yet because the coefficients don't match. So what I'm going to do is I'm going to leave the first equation just as it is, but the second equation I'm going to multiply by 2. And that's a nice easy way to write that. You can just say leave pi 1, but pi 2 I'm multiplying by 2. So 3x and then here's the second one. And I'm multiplying everything by 2. And this time, like I said, we're going to try and eliminate the z's. So I have a plus 4 and a minus 4. I should be adding these equations again. So this time I'll get 5x plus y. The z's are gone. Plus 5 equals 0. And I want to rearrange this again so that the y is by itself. So I'll put the y there. And I'll have a minus 5 minus 5x. So this looks pretty good so far. We've got everything rearranged fairly nicely. I want you to back up for just a second and remember what we had before. We're trying to get that as an answer. I feel like I've made a mistake. I'm going to pause for a second and see if I can find it. I found it. So I'm starting to realize that I'm getting really bad at making these little mistakes. It was right here when I multiplied again. I put a plus 12 equals 0. I'm guessing you guys all caught this because you guys seem to be way smarter than me. That should have been plus 10 equals 0. And that changes things around a little bit. That's going to make that a plus 3. And then that becomes a minus 3. Sorry about that. I hate it when I make those mistakes. So here's what we have. We know that y is equal to minus 3 minus 5x. And we know that z is equal to 1 minus 2x. And we don't have anything for x, do we? I mean, x is just x. And yes, I wrote it like that for a reason. That's what I've got so far. And again, I want to back up for just a second and take a look at what we had on the previous slide. We said this was the answer, right? That was supposed to be our answer right there. So if that's our answer, how does that match with what I have here? Pretty close, right? The difference is that instead of having the x, we've got a t. And so, in fact, what we've done is we've found the answer. This is our answer right here. The problem is that we didn't have a parameter, right? We didn't have a value of t. So the trick to this question is we just have to introduce a parameter. We need to put one in there and say let t be something. So we say, very simply actually, we just say let x equal t, our parameter. We're allowed to do that. This seems like we're cheating a little bit. At least it feels like it to me. We're saying, no, let's just let our variable be something else. That's okay. But we're allowed to do that. They're still variables. It's just representing a place where a number can go. And so that works. And if I write it down then, x is now equal to t. And y is equal to minus 3 minus 5t. And z is equal to 1 minus 2t. And if you want, you can put this back in, 0 plus 1t. You don't need to have it there, but if it looks a little bit better, you certainly can put it. That's how we find the equation of a line. And so, I don't know, I've always found this lesson a little bit frustrating because you look at it and go, seriously, did that really work? And that's why we verified it in the last step, right? We proved that really was the line of intersection. So this is the steps that we need to follow in order to get there. So it works relatively well. But when we're doing the questions in the future, you're not going to want to check it. You don't want to check it every time. You just want to get the answer and go from there. So we're going to try a couple more of those. At least one more in a second. These two are a little bit different. These are actually the easier examples. So here it says, can we tell simply by looking at the equations? Can we just look at the equations and understand what we're looking at? So it says determine if the planes intersect or not. Can we tell just by looking? This is a lot like the warm-up we just did, right at the very beginning. Take a look at those two equations and do you notice anything? Is there any pattern in the numbers? And I hope what you'll see there is that if I take the first plane and I multiply it by minus 3, then I actually get the second plane. Exactly, right? Everything lined up. 3x times minus 3 gives you minus 9x. Even the number at the end, the minus 4 times minus 3 will give you the 12. So what that tells you is that that first equation of the plane and the second equation of the plane are exactly the same. So we have the same plane. And if there's the same plane, technically then there's an infinite number of intersections because they're right on top of each other. Right? So that's our scenario there. That's a good one for us, right? We just look at it and say, oh, look, they're the same plane. And then here's the other possibility. And so you take a look and say, well, are they the same plane? And it's close, right? Everything seems to work relatively well. 3 times 2 is 6, minus 1 times 2 is minus 2, 2 times 2 is 4, but it doesn't work there. So are they the same plane? No. But those coefficients, the 3, the minus 1, and the 2, that represented our normal vector, right? That was our a, b, and c value in the scalar equation of the plane. So both of these planes have the same normal vector, or at least parallel normal vectors. So these two planes are parallel themselves. Now, I have to write that a little bit differently because I can't say this anymore, right? That's not true. 2 times pi 1 doesn't give me pi 2. It's just a normal vector. So the way you write it is you'll say 2 times the normal vector, right? Just n for normal vector of the first plane is equal to the normal vector of the second plane. Therefore, the planes are parallel. And therefore, there's no solution at all. So those are good cases for us. We're hoping for questions there because that's just a case of looking at the equation right away and recognizing it. You should do that every time. So for every one of the questions, look for that first. Some people won't. Right? You'll start doing a whole bunch of algebra and then go, oh, shoot, I should have known that right away. So here's our last one. It says, determine the intersection of the planes, if any. And I usually word it like that, saying if any, because I don't want to give it away. So that's saying there might be intersections, there might not be. You have to figure that out. So first thing we want to do, just take a quick look at the equations and see if they're multiples of each other. Notice I've written them a little bit differently. I took the constant term and moved it to the right. I find that's actually a little bit easier to use that way. But it doesn't matter, you can go either way. Are they multiples of each other? Definitely not. It's easy to tell, right? Just look at the x's. The x's were multiplied by -1, but the y's were multiplied by 3. So they're clearly not multiples of each other. That means there must be a line of intersection. So now we're just trying to find that line. What we have to pick is which variables we want to eliminate. So we're going to eliminate 2, right? What we had done before was we eliminated y and z and wrote everything in terms of x. And I picked that because they were the easiest 2 to eliminate. You don't have to eliminate y and z. You can eliminate any 2 variables that you like. And of course, we're smarter picking the easiest 2. So if you look at this and say, okay, which variables are easy to eliminate? The x's for sure. So we're going to eliminate the x's. And then our next best bet is the y's. So eliminate the x's, eliminate the y's. And then we're going to write everything in terms of z. So we're going to eliminate the x's, we're going to eliminate the y's, and then we'll have to rearrange. So let's set that up here. Here's our first one. We got 2x plus y minus 3z equals 10. And this is our easier one. We're going to eliminate the x's. Since we've got a +2 and a -2, we should add these together. So we got 4y plus z equals 25. And if it's okay with you guys, I'm going to come back to that in a second. I'm actually going to eliminate in the other one as well because I want you to see something. For the other one, we're eliminating the y's, right? Yes. So we need 3 pi 1s, and don't change the second plane. So 6x. Hopefully I don't screw this one up. And this time, it's a +3y and a +3y, so we should be subtracting. So we're going to get 8x. What's that? -9 minus 13z, not a very nice number, equals 15. And what we want to do is we want to write everything in terms of z. That means we want z to be on the right. We want the y written by itself, and we want the x written by itself. So the reason I didn't keep going with this blue one yet is because I think, don't write this down, I think what everyone would have been tempted to do was to do this, because it would have been easy. But if I do that, when I get over to the green equation, there's no y there, so I can't put y on the other side. The thing that's in common, which is the z value, is what I need on the right. So I'm going to do this in a couple steps. 4y equals 25 minus z. And now I need to divide both sides by 4. This is getting ugly. right? We're not used to this, and I've even told you before that if you start getting ugly answers, we've probably done something wrong. It's not the case here. We've done great. Right? Everything's worked out really, really well. We're going to get a fraction answer, but that's okay here because we're actually done with it. Like as soon as that fraction appears, we never have to do another calculation with it anyway. Looking at this other one, we have 8x equals, whoops, it should be, yep, 15 plus 13z. And we have to divide both sides by 15, or excuse me, by 8. So horribly ugly numbers. But we don't care that they're ugly numbers. It doesn't matter to us. That's going to put us in this position here. We've got x equals 15 over 8 plus 13 over 8 z. We have y equals 25 over 4 minus a quarter z, and we have z equals z. So that looks just like our parametric equations. We're going to let z equal the parameter because we have all three of the variables written in terms of z. And so therefore the line is this. And as I said, you've got those fractions, but all I have to do is write them down again. So it made no difference that I got the fractions. There's our line. And you remember I said a second ago, we're really not interested in checking to see if that really is the line of intersection. You could, right? You could sub those parametric equations back into our originals up here and see if they actually, if it would prove that they're the line of intersection, but I don't think you want to do any work with those fractions. It'd be a little bit miserable. Something to keep in mind, as I say, that's a good answer. We did really well on that question. And I even like the choices that we made in terms of getting rid of, we eliminated the x and then we eliminated the y's. Keep in mind that wasn't the only choice, right? I think it was the best choice, eliminating the x's and the y's. You could have eliminated the x's and the z's, or you could have eliminated the y's and the z's. So there's three different routes that you could take for this question. What that means then is that your three different answers at the end are going to look significantly different, right? Depending on what you choose to eliminate. This part right here, where you pick a variable to be t, if you had eliminated different variables, you might have let y be t or let x be t. So if I put two people and say, each of you do this same question, you could very easily get completely different answers, okay? And I think when this one was originally made, because I stole it from somewhere, I don't remember where I got the question. I think if you eliminate two different values instead, I think it's if you eliminate y and z, maybe it's x and z, I don't know. If you eliminate two of them, you can end up getting to a point where the line actually turns out nice without fractions, right? It's possible. But because we chose the ones that we did, we got some not so nice numbers. Okay. The only reason I mention that is if you're checking the answers in the back of the book, it's possible that you'll see one answer that looks different than yours. So just make sure you take a look at it and recognize that maybe you still do have the same answer. The only thing that should end up being the same is the direction vector of the line. So if you consider just those coefficients there, the 13 over 8, the minus 1/4, and then the plus 1, any other line of intersection, the direction vector should be a multiple of that. So the direction vector that we have is 13 over 8 minus 1/4 and 1. But if someone else had an answer and their answer looked like this, I'm going to multiply everything by 8. 13 minus 2, 8. That could still be the same, right? In fact, almost guarantee you that it is. The direction vector is just a multiple of itself. So if you see that in the back of the book, that's a really good sign. It means you probably did get it right. Okay? A tricky day today. Just the calculations that we have to do are, well, they just feel different, right? They don't look the same. as the type of calculations we've done before. And at least for me, it feels a little bit unfulfilling to find the line of intersection. It doesn't seem like we should be done until you get a complete number answer. But as I say, we did it well. This is how you have to do this type of question. So coming up, we're going to look at how to find the intersection of 3 planes at a time and what that might look like. So try the homework for today, but maybe as you're working on that, also consider the possibility of what would happen if we added a 3rd plane to the situation.